Okay, so we'll get started just so we are on time. Our first talk is on logarithmic width suffices for robust memorization, presented by Amit Sur. Yeah, please go ahead.
Right, so thank you. Yeah, my name is Amitsur Egozi, and I'm going to talk about robust memorization. This is joint work with Gilad Yehuda'i and Ohad Shamir. So the problem of memorization plays a central role in the study of the expressive power of neural networks, where we can define it in the following way. The goal here is to find what is the minimal size that an architecture has to have so that it can robustly, that it can memorize every multi-class data set of size n in RD. Where here we say that the network memorizes the data set if it perfectly fits the data. That is, if for every sample xi, the network assigns the correct label yi. And yeah, this is a very well-studied problem with many works establishing results both on the number of parameters that are required and the width and the depth of the network. But notice that there could be many possible ways to fit a specific data set, and not all of them might behave in a desirable way outside of the data points themselves. And so the requirement of only memorizing the data points themselves is not always sufficient, because we want predictors to be able to handle real-world challenges, namely handling noisy inputs or withstanding adversarial examples and generalizing to unseen data, all challenges that require a well behavior outside of the data points themselves. And so this motivates the following modification of our goal, where now we want to find what is the minimal size that an architecture has to have so that it can robustly memorize every size n data set in RD. Where here now we say that the network R robustly memorizes data set, where R is the radius, if not only does it perfectly fit our data samples xi, but it also assigns the correct label to all the points within its R neighborhood. So here, for instance, we have a data sample xi, which is an image of a dog, and a robustly memorizing network would assign the correct label of a dog also to a corrupted image or a noisy image of the dog that is within R distance from the original sample. And so in the case of non-robust memorization, that is with the width, the radius is 0, it has been shown that a network with width of k less than or equal to 12 is both a necessary and a sufficient condition. Whereas in the case of optimal robust memorization, that is where we want to memorize with the maximal possible robustness radius, then a width that is theta d is both a necessary and a sufficient condition. Here I remind you, d is the input dimension. And so what we ask is basically what happens in between, right? So what width k is necessary and sufficient in order to memorize any data set with a given robustness radius r. And so our results show basically the characterization of the width and conditions on when it is necessary and sufficient. Importantly, notice that a width that is logarithmic in the number of points n is both a necessary and a sufficient condition to robustly memorize. And in particular, it follows from these two bounds that if you want to robustly memorize, you can do it with any width that you desire, as long as the radius of robustness scales like the number of points to the power of -2 over k, where k is the width. Yeah, and we can summarize visually this, what I've been saying. So we can see here in red cases where robust memorization is not possible, in green where it is possible, and the relation between the radius and the width, where in the range between the constant width and theta d width, we see that robust memorization is possible only when the radius scales according to our bounds. So how do we prove our main results? So we use the following observation, that in order to robustly memorize with a network that is with width smaller than dimension d, then the first layer of that network must involve a linear map that maps our input samples from RD to a lower dimensional RK. But it has to do so in a way that the neighborhoods of those data samples are mapped to disjoint set in RD. Otherwise, any point in the intersection, we will not be able to classify correctly. So we say that a map is an R-preserving map of a data set if it satisfies this requirement, and we capture it with the requirement that the differences between points from different neighborhoods do not contract. And so now we can frame our problem in the following way. We ask under what conditions can we guarantee that for every data set, no matter its configuration, there will always exist a linear map to RK that is preserving in this way. Yeah, so notice that this preserving map bears similarities, but is not equivalent to the map that is guaranteed by the Johnson-Lindenstrauss lemma. And this is because the Johnson-Lindenstrauss lemma deals with the finite samples, and it can guarantee the reduction of the dimension with an approximate isometry. But this does not necessarily follows for the entire neighborhoods of these points. As we can see in this image, where points in the data set X and X prime are mapped to points in RK that are exactly of the same distance, but their neighborhoods now intersect. And so what we do in our work, we prove an adjustment to the Johnson-Lindenstrauss lemma where we can characterize when such preserving maps exist, and we show that when the radius is small enough, then for every data set, no matter its configuration, we can always guarantee a preserving map to RK. And on the other hand, when the radius is too big, then there will always be a data set that cannot be preserved. Now, using this theorem, we can now characterize the behavior of robust memorization, because this preserving map would serve as the first component in any robust memorizing network that we'll have with K. And lastly, notice that these two bounds are almost the same, where we have a gap of a dependence on the ambient width d, the square root of d, and this gap is the reason for the difference between our bounds in the main results. So just to summarize what we've seen, so our work studied the trade-off between the width and the robustness radius for robust memorization in Rayleigh networks. We showed that the robustness radius decays like the number of points to the power of -2/k. And so if one wants to robustly memorize with a constant width, it cannot be done with a radius that is independent of the number of points. If one wants to do that, that is to robustly memorize with a radius independent on the number of points, then a logarithmic width that is scaling like a width that is scaling like a log of n is both a necessary and a sufficient condition. So just to mention a few possible directions for future work, so finding tight bounds for the preserving map theorem is obviously one thing that can be studied, and also note that we focused on the width, optimal width of networks, and their relation to robustness radius, but future work can be focusing on the number of parameters and its relation to the radius of robust memorization. Yeah, thank you for listening.
Okay, we have time for perhaps 2 questions.
Yeah.
Do you have a explicit construction, or is it critically depend on the ReLU activation?
So basically, you guarantee with probability not zero that there exists a random projection that will, no. Any more questions?
I guess I have a question. So
Okay.
are the results specific, do they hold for any norm, like in RD, or are they specific for L2?
Right, so
or?
in these slides I focused on our L2 norm, but in our paper we generalize to any LP,
Okay.
even P smaller than 1, so like
Okay.
semi-norms.
And what about, what if we relax the requirement to be like, I want to memorize 1 minus epsilon fraction of the data?
Yeah, so that's also an interesting question that
Yeah.
can be extended, like in probability, can we guarantee that
Yeah.
maybe some intersection will occur? But yeah, so this could be a good direction for future.
Okay, cool. All right, let's thank the speaker again.
Thank you.
Can the next presenter Okay, so the next talk is on agnostic learning of arbitrary ReLU neuron under Gaussian marginals, presented by Aravindan.
Hi, everyone. So this is some work on learning a single ReLU neuron. This is joint work with, I'm Aravindan Vijayaraghavan. This is joint work with Bob Guo, who's a PhD student in Northwestern. Bob actually did a lot of the work. It's unfortunate that he couldn't be here for the conference to present the work. These are slides that are mostly made by him. If you want to see a better version of the talk, you should go online and see his talk. So let me first start out by telling you a little more about the ReLU neuron. I'm sure all of you know it, but just so that we are all on the same page. Of course, neurons are the building block of modern neural networks. For a neuron, you need to specify a weight, a bias, and the activation function. Okay, and the most commonly used activation function is the ReLU, or the rectified linear unit, which is basically like a linear function, two linear functions, which is with a switch at 0. Okay, so this is the ReLU neuron, in general, you have parameters for the ReLU neuron. So there's a weight vector W and a bias B, which is a real number, and given an X, which is an n-dimensional vector, it's going to map it to a real number given by this activation applied to the projection along W plus this bias. And this weight vector W and the bias are the parameters of the neuron, and the goal is to learn a good fit neuron for your samples. Okay, so that's a broad goal, and of course we all know that there's a big disconnect between theory and practice. But just to give you a sense of this disconnect, right? So in practice we use variants of gradient descent to train gigantic neural networks with millions of neurons. I have to say it works pretty well. On the theory side, we don't have any efficient polynomial time algorithm that can provably learn even a single neuron, okay, with good fit. So we're going to focus on this side, on the learning theory side, and our focus is mostly on learning a single ReLU neuron, giving polynomial time guarantees for fitting a good ReLU neuron to your data. Okay, so let's go into the formal question. So this is formally in the agnostic learning model of the problem. Okay, so you're given access to IID samples from a distribution. X comma y are feature label pairs. Okay, X is in Rn and Y labels, real number labels. And the marginal distribution over X is assumed to be a standard Gaussian, and this is for reasons that I will mention in a bit. Okay, and our goal, and this is supposed to mean that the marginal distribution over X is not too bad, and here we're going to assume that it's Gaussian. And your goal is to output a function which predicts Y. Okay, and here there are no assumptions being made on Y, and this is what is usually called the agnostic setting or the non-realizable setting, or to fit with the robust learning session, the adversarial label noise setting. Okay, and the goal is to basically find a neuron or a function f in general, but we'll fit a neuron which fits your Y up to small error measured in the least square sense. Okay, and sorry about the transitions. So when converting from PPT to PDF, some of these transitions went away, but maybe I'll finish earlier than expected. So our goal is to find a neuron that is competitive with the optimal fit that's possible, where opt is the neuron that achieves the least error in terms of the least squares error. Okay, and for the purposes of this talk, you can really assume that the weight vector is a unit vector. It's really a scaling issue. You can figure this out. And you can also assume that the bias is known because you can always guess the bias. It's one real number. Okay, so you can just think of the weight vector as being this hidden unit vector that you need to kind of find. Okay, is the problem clear? Okay, good. So just to give you a sense of the previous works, so this problem already for a single neuron is already quite hard. Okay, and you have to make assumptions both on the marginal distribution of X. So if you don't make any distribution assumptions, you can't hope to get any competitive guarantee with opt. Okay, and that's a result by Dijk, Nicholas et al. And also, you can't hope to get a guarantee of the form opt plus epsilon. Okay, you need to lose at least a constant factor. Again, there are computational evidence of computational hardness due to a different paper by Dijk, Nicholas and others. Okay. So we are going to assume Gaussian marginals, and we're going to aim for order of guarantees. Okay, and in terms of prior algorithms, so there are prior algorithms that solve special cases of the problem. So the zero bias case, which is also called the homogeneous case, has been studied a lot. It's also been studied under this the space of single index models. And people also look at bounded bias or positive bias. And these are things for which you can actually prove that gradient descent actually works, okay, with random initialization. But all of these algorithms are based on gradient descent, and they all fall into this class which is called correlational statistical query algorithms. Okay, you don't need to know what this class means, but it's just a very reasonable class of algorithms, and moderately biased ReLUs fall into this class. Okay, so this is the prior state. So we know algorithms for special cases, and we don't know the general case of the problem. And that's the main question that we address. Is there a polytime algorithm for agnostically learning arbitrary ReLUs, making no assumptions on the bias? Okay, oh, okay, so the suspense is already here. So the second question is it actually harder than the moderately biased case? And the answer is actually yes to both, which is kind of interesting. Okay, so we do show that there is a polytime algorithm, but it's not a CSQ algorithm. It turns out to be an SQ algorithm. Okay, so let me tell you more about the results. So the main result is just a very clean statement. There's an SQ algorithm that runs in polytime and gets an order of guarantee for this agnostic learning problem. But here again, remember that these are Gaussian marginals. It's not general, and you need to make such an assumption. Okay, and this is a polytime guarantee. So no assumptions on the ReLU activation. Okay, and it turns out that no CSQ algorithm can achieve such a guarantee. So any CSQ algorithm needs to use either super polynomially many samples or take exponentially many CSQ queries. Okay, so typical variants of gradient descent cannot achieve an order of guarantee. So there's a different algorithm that we get that achieves this order of guarantee. And to some extent, this is arguably the simplest separation between SQ and CSQ style algorithms. Such separations have been known from this work of Chen, Kalai, and Meka for pack learning, single layer neural network with many neurons. But this is arguably the simplest separation. I should also mention that more recently, subsequently, Zarifis et al. Had this really nice result, which actually gets a similar order of guarantee, but for a more general class of activations. Okay, I don't know if they get the lower bound, but yeah, they get this much more general algorithmic result as well. So maybe I'll just give you a little bit about, in a couple of minutes, tell you a little bit about why gradient descent fails and what we do. Okay, so gradient descent looks at the gradient of the loss. Okay, and roughly speaking, what the gradient does is it has a component that's along the current weight vector, and then it has this other component which is roughly along, the expected value of y times x. Okay, it's not quite right, but it's almost that. Okay, and your hope is that when you do this iteration, maybe starting from a random initialization, your hope is that this iterate moves closer towards W star, which is like this hidden direction, the direction that corresponds to the optimal ReLU neuron. Okay, and this is actually what the previous algorithms that analyzed the zero bias case or the moderately biased case do. Okay, it turns out that this doesn't quite work when you have highly negative bias. Okay, so when you have highly negative bias, what happens is you see a lot of zeros, and then towards the end you see the spike. Okay, that's what highly negative bias means. So W transpose X needs to be very positive to account for the negative bias. Okay, so and then it becomes really challenging. And in fact, you can construct this bad example. Yeah, I'm sorry for a lot of the text being thrown at you, but I'll try to get through this. So you can come up with this example where any solution which gets a constant factor approximation must get the right direction. But then the label noise, which really dominates this correlation, the expected value of y times x. So this small amount of label noise that you can add to the left of 0 and blue can actually dominate the signal. Okay, and so you don't actually get the right direction. And so gradient descent fails, and you can actually convert this kind of intuition to get CSQ hard instance as well. And what we do is we actually come up with a two-stage algorithm. The first stage, which is the non-CSQ stage, is to do some kind of a threshold at TCA. So you look at all samples where y is larger than some value, and then you take the PCA direction there, and that gives you some kind of an initializer towards the right direction. It doesn't give you the right direction, it gives some kind of a, its distance from the right direction is little over 1, and then you can then refine it using not just gradient descent, but you need to be cleverer, you need to do this reweighted projective gradient descent. But somehow you have to reweight the distribution to shift the Gaussian center towards the threshold. Okay, so then it becomes more like the moderately biased case, and then we can actually prove guarantees. So and this is like an iterative algorithm, and this modified version of gradient descent can actually refine and find the right signal. Okay, so just to summarize, we give a polytime algorithm for learning a single ReLU neuron under Gaussian marginals, and this is in the agnostic or non-realizable case. And this is a SQ algorithm, and interestingly, no CSQ algorithm can achieve such a guarantee, so that gives a nice separation.
Thank you. So we have some time for 2 questions, perhaps. Any questions?
So what determines if a bias is moderate or if it's too large?
Moderate just means the bias is bounded by a constant. So really, you have to look at the bias divided by the norm of the weight vector. If it's a constant, then
So, but if it grows with dimension, then it's like too large.
Yeah, it's too large. In general, you don't need to worry about biases which are larger than, let's say, if you're aiming for an additive error of, you're incurring an additive error of epsilon, you don't need to worry about biases which are larger than root log 1 over epsilon, because then you're never going to see those points. But, there's a big gap between bias of 2 versus root log 1 over epsilon.
Okay, thanks.
Any more questions?
Can your technique or your algorithm, can you think of ways you could generalize it to other distributions, or if you looked at other well-behaved non-Gaussian marginals?
That's a great question. So, yeah, I think it would be great to, I think in general you can't hope for a distribution-free guarantee, but I think it should be possible to generalize this to things more than Gaussians. We certainly need some anti-concentration, some concentration properties too, but I don't know a nice sufficient class of distributions. And also, it will be great to generalize it to more than 1 neuron. Clearly, we don't learn just 1 neuron in practice. Yeah, it's a great question.
Okay, let's thank the speaker again. Can the next presenter show up? Okay, so next we have simplifying adversarially robust back learning with tolerance, presented by Vinayak.
Thank you. I'm Vinayak. Yeah, and that's the title of my talk. Okay, what am I supposed to press? Yeah. Should it? It's not working. Okay. Yeah, so this is joint work with Ruth, who's sitting right there in the audience, and Hassan, who's probably still enjoying temperate summers in Toronto. This was supposed to appear one by one and be more dramatic, but this is the outline of my talk. I'll quickly go over pack learning, then define adversarially robust pack learning, then explain what's with the tolerance business, and finally present our own result where we simplify something, and I'll explain what. Okay, so pack learning, I'm pretty sure everyone knows what it is, but just to quickly recap, it's a framework for analyzing supervised learning. It has, we assume there's some unknown distribution P that generates labeled examples. There's a learner that can look at the examples and has to return a hypothesis. And we measure the learner's performance with this binary classification error. And so little l and big L are Little l is the pointwise error, and big L is the expected error. And there's this other thing that we have to encode. We get to encode our domain knowledge about the problem using a hypothesis class H that we think contains a hypothesis with low loss. And the goal of the learner is to find a hypothesis that matches the loss of the best hypothesis in this class. And we give it a little bit of slack epsilon because it's doing that using just a finite number of samples. And we know that this problem is characterized by the VC dimension of the class. Now, the adversarially robust back learning problem was born out of this empirical observation that basically assume that H is some state-of-the-art model. It's been trained using whatever is the best method. And then what's found over and over again is that you pick the points X in your data set. And so H will correctly classify a large percentage of them because it's a SOTA model. But you are able to find these Zs that are in a close neighborhood of X where the H changes its opinion of the label. And so this does not align with our domain knowledge. We do think that for most of the points, small perturbations should not change the label. And so a slightly different problem was formulated probably a decade ago to understand this theoretically. And that's this pretty much the same thing as the one in the previous slide, except we changed the loss function a little bit, where we penalize the hypothesis not only if it misclassifies X, but also if there is some Z within a small neighborhood of X, where H gives it a label that's different from the correct label of X. And so the LU and the little LU and the big LU are the corresponding losses for adversarially robust back learning. And once again, the learner's goal is pretty much the same, except we replace the loss function with the LU. This turned out to be a very difficult problem, and a sequence of results. I think pretty much all of these results have Omar's name on them, and these results prove that this problem is hard. For example, VC dimension no longer characterizes it. The best characterization is fairly complex, involves defining these infinite graphs. ERM doesn't work anymore. Proper learning doesn't work anymore. And you can do improper learning, but the sample size becomes exponential in VC dimension. And so the question is, can we find a simple learner that can do adversarially robust learning with sample complexity that's polynomial in VC? In 2023, we had a paper with the same co-authors where we added this concept that we call tolerance. And the idea was that maybe the way we are defining this adversarially robust back learning is too hard, and maybe a more relaxed version exists where we can show these kinds of guarantees that we want. And so, and the intuition behind that was, in reality, we do think that perturbing the label, the point a little bit should not change the label, but we don't have a precise definition of what that little bit should mean. And so basically we don't really care about whether we change 5 pixels or 6 pixels in your image, but we do think that some small number of pixels should not change your label. So to encode that into the problem, we came up with this tolerance where suppose you have 2 different perturbation sets, U and V, and where Ux is a subset of Vx for all x. And then we want, in the end, to get that sort of guarantee where you are measuring your hypothesis, the loss of the hypothesis in terms of LU, but you want it to match the loss with respect to LV. And the idea was that this problem should be easier. We indeed showed that if your smaller ball U is a ball of radius R, and the bigger ball V is a ball of radius R times 1 plus gamma, then you do get a polynomial, a sample complexity that's polynomial in VC. The ambient dimension and this tolerance parameter gamma, or 1 over gamma. And then, but the algorithm was fairly complex, involved compression schemes and whatnot. At the same time, another paper showed up that analyzed the tolerance framework, and they showed that you can get a fairly simple algorithm to get the same sort of guarantees, but it required an additional assumption on H. H had to be what they call regular. So in this paper, we show an algorithm that has these properties. First, it's in some sense simple. It's almost proper, so it doesn't, in the sense that the hypothesis that it returns is very similar to some hypothesis in the hypothesis class. And it achieves the same guarantees as the previous algorithm, and it does not require any additional assumptions on H. Okay, so to convince you that it's a simple algorithm, I'll present it to you in 2 steps. So first step is basically you do this sort of empirical risk minimization, but with respect to this the LV loss function as opposed to the binary classification loss function. And once you have your the output H hat, you smooth it. And the meaning of smoothing here is that you you consider this little ball of radius gamma. Remember, gamma was the tolerance parameter. So this ball is pretty small. And you look at the majority label within that small ball around your X. And that's your answer. So that's it. That's the, if you return H tilde, the smooth version, as opposed to the H hat, the claim is that this has the guarantees for the tolerance framework. Okay, let me just state the other results, and if I still have time, I'll highlight the proof sketch. So the other result is, so that was just for the realizable case, by the way. And so we also have a very similar algorithm that also works in the agnostic case. And then we have algorithms for the semi-supervised case as well, where a previous result showed that you can solve the original adversarially robust learning problem with unlabeled sample complexity that was exponential in VC, but the label complexity was still polynomial in VC. But the algorithm involved invoking some fairly complex subroutines from previous work. And we have a much simpler version of it, and that achieves almost the same guarantees. Now, okay, so how much time do I have? One minute or so? 30 seconds? Okay, so in 30 seconds, I'll present the proof. So there is a result from Atias et al. That says that if you go back to the original without tolerance setup, and you assume that your V, the perturbation, the set of neighborhood was finite, then you need those many samples, VC times log of K, where K is the size of your set of perturbations. And so the idea here is that if your Vx is not finite, then you still have, if your V is not finite, just imagine that there is some finite subset of V that we are calling C. And if you run the empirical risk minimization from the slide, you get that guarantee on C because it's finite. And while I'll not go into the details, but if you only have a finite number of points within your Vx that you know have the same label as your center X, and what you want is any small ball of radius gamma that you're taking the majority within that small ball should match the label of one of these points in this finite set, and that's roughly the proof. Hopefully, it made some sense. Okay, I'll stop here.
All right. Any questions? Okay, perhaps I can ask a question. So do you have any idea on, in terms of, for lower bounds, whether this achieved sample complexity bound is tight, or at least the dependence on this gamma parameter?
Yeah, no, I don't think we have. No, we haven't thought too much about lower bounds. But yeah, that's something we should. Yeah.
Okay, let's thank the speaker again. All right, so next we have a talk on adversarial examples for random convolutional networks via isoparametric inequalities presented by Amit Danieli.
Okay, thank you. Okay, so the talk is about adversarial examples. I guess most of you have heard what adversarial examples are, but let me just quickly go over that. So adversarial examples are rather, I would say, peculiar phenomena, so that you have some examples, say an image, and you can slightly perturb this image. Okay, you can add it a very little bit of noise or some vector, so that a human won't be able to tell the difference. Still, this perturbation completely confuses the network, and instead of predicting panda in this case, it can predict Gaibon or airplane or piano or whatever you want. And it turns out in the last decade that this phenomena is quite common in neural network. Usually when we train a neural network, this phenomena happens. We have an example, we can usually perturb it very little so that the network is completely confused. And this raises many questions. For example, one question is how we can prevent it. We definitely don't want this phenomena to happen. It might be a security threat, and it's definitely not desired. And even a more basic question is why do we see this phenomena? Why this phenomena happens? And there were several attempts to answer this question, to explain why this phenomena happens. And one such line of work developed by people from the code community provides some, at least some partial answer that explain this phenomena. And it shows that for many architectures, random networks do suffer from adversarial examples. So what do I mean by that? Let me be a bit more precise. Suppose I have some example, then I choose some neural network at random. Then with high probability, I can slightly perturb this example to change the sign of the network. Okay, so this is a line of work. I won't go over all the results. I'll just explain you what's our contribution to this line of work. So I think we have two contributions. The first one is, I think, the first extension of such results to convolutional neural network. So previous results mostly concerned the fully connected neural network, and we extended it to convolutional network, which are more natural in this context because these phenomena usually take place for images or sounds, and these are trained using convolutional network. And the second contribution, which is going to be the focus of this talk, is that we have a very simple proof of why this phenomena happens. And I'll dedicate the talk to show you this proof, and I hope that in 5 minutes you'll all understand why this is happening, at least in random network. Okay, so let me jump into a bit more technical details. So first, I need to define what's random networking. So I'll focus on the fully connected case. For simplicity, I won't talk about convolutional neural network. And the first thing that I'll need to define is what do I mean by a random network. So usually, in order to define a random network, I need to define a structure and activation function and the way I choose the random weights. But here I'm going to take a relatively general and abstract perspective of what random neural network is. So a random neural network is just a random function from our instance space, which is going to be the sphere in d dimensions, 2R. Okay, it's a random function, which is which is rotation invariant. Okay, what do I mean by rotation invariant? It has the following property. This distribution on function has the following property. If I take a rotation matrix and compose it with my random function, I get a new random function, and I require that the distribution of these two random functions is identical. Okay, so if I take a random network and rotate it in this way, then I'll get the same distribution. And the primary example for such a random network is a random standard multi-layered network with weight initialized using a standard way, like a Javier initialization or orthogonal initialization. But it's not the only example. For example, if you take a multi-layered network, you initialize the first layer with random Gaussians, and then you do whatever you want in the remaining layers, you still get a random network according to this definition. Okay, so this is a random network. And what is an adversarial example? So I'll define a notion which I call an attackable example. Attackable, I mean that this example can be attacked, meaning that I can find a small perturbation of this example that change the label of the network F. Okay, so an example is attackable if there exists another example, X prime, such that the label of X prime is different from the label of X. This is one requirement. And the second requirement is that X and X prime are close. Okay, so the second requirement is that the distance between X and X prime is smaller than epsilon, and I'll fix epsilon throughout this talk to be the square root of log D over D. Okay, this is the epsilon we take. This is, as a side note, it's optimal up to this log factor. Okay, and the main result tells us that if we take a random network F and some fixed example X, then with high probability this example is attackable. I can perturb it a little and change the label of the network. Okay, so this is the result, and I want to explain how this result is proved. So we need to define a few additional definitions. So I'll define a notion of attackable set. So my network F divides the instance space into 2 or 3 sets. The first set is the set of negative examples. The second is the set of positive examples. And there is the set denoted here by A and colored red, which is the attackable examples. Okay, so these are examples that I can change a little bit and change the label of the network. So these are either negative examples that are very close to some positive example, or positive examples that are very close to some negative example. To be a bit more formal, I'll define the neighborhood of a set to be all the points. The neighborhood of a set A is all the points X whose distance from the set A is smaller than epsilon, and I remind you that we have this fixed epsilon. Okay, now I can define the negative and positive sets with respect to F. This is the points that are mapped to plus and the points that are mapped to minus. And it's not hard to verify that the set of attackable points, which I'll call the attackable set, is the intersection of the epsilon neighborhood of the negative point and the epsilon neighborhood of the positive point. And now I can restate our main result, which means that if I have a random network F and some example X, then the probability that X is attackable, that X is in the attackable set, is almost 1. Okay, and in order to prove this result, I need 2 observations. The first observation is quite immediate, is that the attackable set is rotation invariant. What do I mean by that? It means that if I take a rotation matrix, compose it with my set, I get a new random set, and the distribution of these 2 sets is identical. So this is an immediate corollary of the fact that F is rotation invariant. And the second is that the attackable set is large. Its measure is almost 1. Okay, so this is the standard uniform measure over the sphere. So the first observation is immediate. The second observation is a consequence of the isoperimetric inequality, and I'll explain that in the next slide. And these 2 observations implies our result. So we take a random rotation U, and now the probability that X is attackable is exactly the probability that X belongs to a random rotation of the attackable set, because these 2 are distributed identically. I can move U to the left side, so this is the probability that a random rotation of X belong to the attackable set, but the random rotation of x is just a random point, so this probability is just the measure of the attackable set, and the second observation tells us that this measure is almost 1. Okay, so these two observations immediately imply our main result. And I just want to say a few words why the second observation is a corollary of the isoperimetric inequality. So the isoperimetric inequality tells us that for every subset, or every non-negligible subset of the sphere, its epsilon neighborhood is very large. And since the attackable set is an intersection of the epsilon neighborhood of two sets, it's also must be of almost complete measure. Okay, that's all the proof. Let me have a quick summary. So we showed that the existence of adversarial example in random neural network is a relatively immediate consequence of the isoperimetric inequality, and this simplifies some previous work. And second, what I didn't talk about is that this proof extends with slightly worse quantitative parameters and some other technicalities, but it mostly extends to a convolutional neural network. And that's it.
We have time for perhaps 2 questions.
Yeah, so the necessary requirement of the space, domain space of the function has to be like a compact set, like the sphere, or is it can be generalized to any other?
It depends. So for the ReLU activation, because it's homogeneous, then it's true for Rn. You don't need to restrict to anything. But for other activation, we might need some restriction.
Did you consider generalizations to neural networks that are not completely random, like trained or something with a little bit more structure than random networks?
So the way we had the structure is to consider convolutional network. So we didn't do that. I think that if you take any network, even one with very small loss, and you take a perturbation of it, then you also have the phenomenon of adversarial example, but we didn't prove it.
Oh, so it won't apply to any network, but you think it will apply to most networks in a sense?
Yeah, no, it's not true for any network.
Yeah, of course.
There are networks that are...
but for most networks?
But for most networks, it's true.
Okay.
That's the take-home message of not our work, all this line of work.
Okay, thank you.
Okay, let's thank the speaker again. Okay, next we have heavy-tailed contamination is easier than adversarial contamination, presented by Yashwant.
Yeah, so I'm going to talk about heavy-tailed and adversarial contamination. And this is joint work with my amazing collaborator, Daniel Lee, who couldn't make it to the conference. Okay, so just for some concrete motivation, I'm going to start with a very basic statistical estimation problem of like mean estimation. So the problem is very simple. I'm going to give you access to n IID random samples that are drawn from like some high dimensional distribution D. And I'm going to assume that this distribution has some mean mu. And for the sake of simplicity, let's just say that it has an existing variance, and the variance of this distribution is identity, okay? And basically what you want to do is that you want to estimate the parameter mu, okay? This is the only unknown parameter of this distribution. And since it's like a mean estimation problem, the natural estimator for you to use in this setting is to simply compute the empirical mean. Okay, and now you can ask, okay, like what's the problem with this solution? Like, it seems like a perfectly well computable solution, and it feels like it should work well. It turns out that the solution turns out to not be extremely robust. So this solution can be like very inefficient if the data that the estimator actually sees is imperfect in some ways. And sometimes in some of these settings, you might not get any guarantees on the performance of this estimator, okay? And I'm going to talk about like 2 recent settings that have received a lot of attention. The first setting is the setting of adversarial contamination. I'll give you some intuition for what this setting is. The second setting is a setting of heavy tail contamination, and both of these have seen a lot of past and recent work on both of these topics. There's been some classical work that analyzes like the statistical performance of some of these settings, but there's also been a lot of recent work on like trying to build like more algorithmic solutions to some of these problems, especially in high dimensional settings. Okay. So let me talk briefly about like what the adversarial and heavy tail contamination settings are. So I'll start with the adversarial contamination setting. So you have these points x1 through xn that are generated from like some high dimensional distribution. And let's say that these are not the samples that you actually see. So what you're going to do is that you're going to allow an adversary to actually inspect all of these n data points, and you're going to allow them to arbitrarily corrupt some fraction of them, okay? So let's say they corrupt like 20% of the samples. And the samples that you see are the samples that you get after like the adversary performs this corruption, okay? And now if you try to use the classical empirical mean in this setting, you're going to get like no guarantees on the performance of this estimator whatsoever, okay? And what the field of like adversarially robust estimation tries to do is that you want to build estimators that are resilient to like any sort of perturbation that an adversary could perform to the data. So no matter what the adversary does to those last 2 data points, you want your estimator to perform well, okay? So that's the goal of adversarially robust estimation. Well, what is the heavy tail contamination setting? It focuses on a slightly different sort of motivation. And it focuses on settings where like these classical estimators, such as the empirical mean, have statistical inefficiencies. Okay, what do I mean by that? So let's say you don't want to be robust to like adversarial examples, but instead what you want is like good confidence intervals for the mean, okay? So you want estimators which have the following guarantees. You want your estimate to be within some radius r delta of the true value mu, with probability at least 1 minus delta, okay? And you want the radius of your confidence interval r delta to be as small as possible, okay? So you want like really tight confidence intervals for the thing that you want to estimate. So how well can you possibly hope to do in this setting? It turns out when the data is actually Gaussian, or it comes from like a super well-behaved distribution, the empirical mean is in fact optimal. So that you can't really construct a better estimator than the trivial one that we saw on the first slide. But what a lot of past work has noticed is that like the empirical mean can perform very poorly if the data is not Gaussian. If it's not so nicely behaved, the guarantees on its performance can be quite poor, okay? But the somewhat surprising thing is that you can actually recover Gaussian-like behavior even in this very non-Gaussian setting. So even if your data deviates substantially from Gaussian behavior, you can build better estimators from within the empirical mean that can recover the same guarantees as if your data were truly Gaussian. Okay, and this is this beautiful result by Lugosi and Mendelssohn from 2017. Okay, so we have like these two different like sort of like estimation problems that work with like imperfect data. First, we have the adversarial setting, where you want to be robust to like adversarial manipulations of your data. And then we have the heavy tail setting where you focus more on statistical efficiency and you want like tight confidence intervals for the parameters that you want to estimate. But despite these two settings having like very different like motivations, we've seen a lot of like algorithmic convergence on both of these topics. So a lot of times like the same or very similar estimator can often achieve both of these goals. It's both adversarially robust and it's going to give you optimal confidence intervals. And we've seen this in the context of mean estimation, linear regression, covariance estimation, and even for clustering. And the natural question that you can ask is, why does this happen? Why are so many algorithms that are developed in one context so easily transferable to the other? Okay. And now I'll tell you a little bit about our work. There's been a little bit of past work on this topic. It's been based on this concept of building like, on this set of algorithms that work on like stable sets within the data that you see. So this is like a framework for constructing robust algorithms. It was developed in the context of like adversarial estimation. But it turns out that a lot of these solutions actually end up working even for like heavy tail estimation as well. So they actually give you really good confidence intervals. But we only know of these results for the setting of mean estimation. And the question that we wanted to ask is like, okay, how necessary is it that these algorithms are stability-based? And what about other estimation problems, such as linear regression or covariance estimation? Okay? And here is our main result. Our main result basically states that essentially any adversarially robust estimation problem, for any estimation problem that you want to solve, is also robust to heavy tail noise. So any adversarially robust algorithm can actually give you really tight confidence intervals. Okay? And our theorem applies to any problem with IID data, so it doesn't have to be mean estimation. As long as your problem is estimation from like IID data, these guarantees hold. And these apply beyond like the specific context of stability-based algorithms that we saw before. And now I'll give you like a brief overview of the proof of our result. So take any adversarially robust algorithm A, and what I want to do is that I want to prove that this algorithm can actually give you good high probability guarantees. Okay, why is this the case? So this algorithm must be robust no matter how an adversary corrupts like some fraction of your data points. So what does that mean? I want the following guarantee on the performance of this algorithm. So what are the different terms in this expression here? X is going to be the true generated samples. So in the context of mean estimation, X is going to be the n IID samples that are drawn from some underlying distribution D. This is not the sample that you actually observe. The sample that you actually observe is X prime. So you allow an adversary to inspect the samples in X, and you allow them to perturb these samples in any way that they like. Okay, so X is what is truly generated, X prime is what you actually observe. And the guarantee on this algorithm is that like no matter how the adversary perturbs X to form X prime, the output of the algorithm is going to be an accurate reflection of the true parameter. Okay? And we want this to be true with high probability over the true underlying samples X. Okay? So it's not going to hold true for every single sample, but like for most samples, this should be the case. Okay, so I'm going to use a little bit of notation here. I'm going to define this following set G, which is going to denote like the good set of samples. These are basically the true underlying samples where like if the adversary perturbs perturbs these samples in any way that they like, the algorithm still outputs like a good estimate of the parameter. And since A is adversarially robust, the set G should have large mass. So let's say the probability of like the true distribution generating a sample from G is at least 90%. And yeah, so we have the guarantee that A is going to be accurate on any sample that's like within some constant fraction of G. So this is simply the guarantee on our adversarially robust algorithm. So why should we expect this to have strong high probability guarantees? We have this guarantee from before, and then this proof is basically going to be by pictures. Yeah, I'm almost done. So let this circle here denote the set of all possible samples that could have possibly been generated by the true underlying distribution. Okay. So you should just think of this as like the set of all tuples of like n data points. And the good set G is going to be like some fraction of the set. And we know that the algorithm performs well when the sample is actually drawn from the set, because it also performs well on any perturbation of the set. But it also performs well on samples that are close to G. It doesn't perform well only on G, but also on sets that are perturbations of sets in G. So it also performs well on a slight expansion of the set here. So the only set of samples on which the algorithm could possibly fail is in this tiny sliver on the right side here. And just going by the theme of like the previous talk, a classical result in isoperimetry will basically tell you that the mass of the tiny sliver on the right is going to be exponentially small. Basically, the idea is that like if I start with a large set G and I expand it by like a constant fraction, the mass that's left behind is going to be extremely tiny. So the probability that the output of the algorithm is accurate is going to be 1 minus something that's like super exponentially small. So you're going to get like extremely strong high probability guarantees. Okay, so that's basically the proof of like the main result of our paper. And I guess in the last minute, I'm going to conclude the talk. We basically show that like any adversarially robust algorithm also gives you very strong high probability guarantees. And conversely, we showed that heavy-tailed estimation is not as strong as adversarial estimation. So any reduction that you want to construct from adversarial to heavy-tailed estimation must basically remove all the points that the adversary has added to the data points. And we can kind of establish this in like some formal sense. And our work also has like several open questions that come out of it. We've shown that adversarially robust estimation is stronger, but we don't exactly know how much stronger. So it raises the possibility that in a lot of settings, we can design much better algorithms for the heavy tail setting than to go through this paradigm of like first designing one for the adversarial setting and just assuming that it carries over to the heavy tail setting. And in the theme of what I just told you, another natural question is like whether we can actually figure out like strong computational separations between both of these problems. Our result is an information theoretic result, but it would be nice if we had like computational versions of some of these guarantees as well. And yeah, with that, I'll conclude the talk, and I'm happy to take any questions.
Okay, we have time for a question.
I was curious if how important is the adversarial contamination model as opposed to, let's say, the TV corruption model or Huber model? Do you think? I mean, yeah, they are comparable to the. Would they imply things for the heavy-tailed case as well?
That's a very good question. We couldn't actually prove that with like a one-step reduction. So the type of reduction that we use is like we get the samples and we directly pass it to the adversarially robust algorithm. If you're allowed to do like multiple rounds of this, then this reduction holds true. But then if you do just one round, like then we don't have this guarantee. But we also don't know that it's like not the case that like this guarantee holds. So we needed like a much stronger notion here, but it's possible that like a weaker notion suffices. Yeah, that's a good question. Thanks.
Any more questions? I guess I have a question on the like alpha, the fraction. How does it translate in the other setting, or like what does it affect? The alpha, like the yeah.
So if you have an alpha parameter, I guess I don't know if I can go back. So if you have like an alpha corruption factor, the alpha shows up in the constant here, so it's going to be alpha square.
Okay.
Yeah. So that alpha square is actually suboptimal, but you can show that like that's kind of necessary.
I see. Okay.
Yeah. So if you do some sort of pre-processing, it's okay.
Okay.
Yeah.
Cool. Okay. Let's thank the speaker again. Can the next presenter show up for faster algorithms for agnostically learning disjunctions? If the author is here, please raise your hand. Otherwise, we'll move to the next talk. Sorry? He will do what? It's going to be on Zoom. Okay, so it will be in a separate session on Zoom for those interested in this paper. And then the next paper will be decision making in hybrid environments. Sorry, what's your name? Julian. Okay, so the next talk, decision making in hybrid environments, a model aggregation approach, presented by Julian.
Yeah, hello, I'm Julian. This is joint work with Haolin, who couldn't be here, and Jenny, who is here in the audience. So this is going to be an RL talk. I don't know, we probably didn't fit into RL anymore, but I hope you're still interested in this. So, all right. So those of you who are familiar with RL, in recent times people had tried to push the boundaries on what is provably learnable, and after having a lot of new sessions, new cases, people come up with generalizations that cover this, and at some point people think there's too much of this and they come up with a new framework, and then you end up with n+1 different generalizations. And our work kind of sits here, but what we ask about, what about adversarial cases? Because most of this work so far had always been done in the purely stochastic case. So let's first talk about the kind of general problem that we're looking at. It's a very general decision-making problem where in rounds 1 to t, in every round an adversary is going to choose a model from some model set M, and independently the learner has to choose a policy, pi. And then afterwards, the learner is going to receive an observation, which comes from sampling from an observation space given the model that the adversary has picked and the policy the learner has picked there. And finally, for each combination of a model and a policy, we assume that there exists a value function. And the goal is to minimize the regret with regard to the best comparator in hindsight. So to make this more concrete for MDPs, or for reinforcement learning, what we're looking at here is a case where our models is always a combination of a transition kernel and a reward function. So our policies are just always going to be mappings from states to actions. So we assume that there's a state space and action space. I hope you're familiar with this terminology here. And then the reward function is always going to map a given state and an action to a reward. And we could also cover stochasticity in the rewards, but here we just assume that a stochastic reward is modeled by just the adversary picking a distribution over deterministic reward functions. And the observation that we're going to see is we just assume for simplicity that there's an initial state and an initial action. And then we're always going to transition into a new state by sampling a new state from the transition kernel. Then the learner is going to sample an action from the policy given that state, and then we're going to receive the reward. And in the banded case, all that we're going to see are these rewards corresponding to the actual state action pairs going to be sampled. And in the full information case, we just receive the full reward function for this round. The value function is just going to be the expectation of the reward over the states and actions with the rollout of this model. So this is kind of how this would work in finite stage MDPs. And one very promising approach to actually look at it in more generality and have some good ways of determining whether something is learnable or not is this quantity called DC, which has been introduced by Foster et al. And there's kind of a range of very similar of these terms, but the one that's relevant for RL here is the so-called offset DC with KL divergence. So this looks a bit complicated, but what it actually says is that given some a baseline mixture of potential models, and these are known to the learner, then the task of the learner is to pick a distribution over policies so that the worst case individual model that can there going to minimize this term here. So we want to minimize the regret that we can, in the worst case, suffer from having a model where the optimal policy for this model is significantly better than the average policy that we play. But we allow this additional divergence penalty to be in our favor. That means that models are getting penalized by how difficult it is to learn them. So how much information would we gain by doing a rollout with our policy over this baseline mixture of models that we know already. So this is, for those who are familiar with this work, is closely related to other frameworks such as the AIR and QSCV or the exploration by optimization introduced by Latimore and Giorgi. And what is known with this is that we can characterize upper bounds and to some degree also lower bounds with this quantity. So upper bounds typically look like that we have this a term that is just dependent on the DEC together with an estimation term, and then these two are just traded off. The lower bounds that exist are typically just the DEC term itself. And for a lot of cases in the stochastic regime, this is well controlled. However, there has been work showing that you can also use DEC to analyze the adversarial case. However, what happens is that you get a dependency on the convexification of the model class. So this is bad news for RL, because in RL, convexification means that we have a mixture of transition kernels. And it can be easily seen that this is typically unlearnable, at least if you don't want to scale polynomially in your policy class, which is typically way too large. And so the question that we're asking there, that we try to make some step forward in answering is, but how can we, in the stochastic case, deal with model-free problems? So if you don't know what model-free is, this estimation term that appears there in the stochastic regime is something that typically scales with the logarithm of the size of the model class. And there are a lot of RL problems where actually the size is extremely large, but we can still learn it because of some other structure, because we only need to care about the dimensions of the Q functions or things like this. So model-free generally here describes learning problems where the size of models is more than exponentially large. And then the other problem here in the adversarial case is, what about hybrid environments? So we know that if the transition kernel is adversarially chosen, we can't really learn it. But in these cases where just the reward is adversarial, we have special cases such as linear MDPs where we know we can actually solve it. So what we are proposing is a framework to tackle these type of problems. We are defining a phi-restricted environment. So this is a subset of a model combined with the policies, and the problem is now that the adversary is going to be restricted in the beginning of the game to have an unknown of these subsets. And then in every round, the adversary can only pick a model and here a comparator from there. For this talk, I'm just going to assume that the comparator is static, so we only have a single policy in each of these sets. And as an example, what I mentioned before, an MDP with adversarial rewards, but that stochastic transitions would be one where the aggregation is such that we always have the same policy, the same transition kernel, but the reward can be chosen arbitrarily in every round. So we have a general algorithm to solve these type of problems. So it is based on the measure air, which comes from the prior paper from Chu and CV. It looks quite similar to the DC term. It is just that we have a prior over these sets phi, and we gonna assume that there's some distribution over which we're gonna sample a new model and a comparator, and then we want to then we look at the difference in regret that we would suffer given that there's this model and comparator sample from there, minus how much the information gain that we get over our prior of these sets where the adversary was restricted in with just a simple Bayesian update. And if you don't know this, it's going to be quite complicated, but what it allows us to have this kind of conceptually at least simple algorithm where in every round we're going to solve a saddle point problem where we pick a distribution over policies and a distribution over possible actions of the adversary that minimizes this term. And this allows us directly to give a bound that's just the size of this sets of possible aggregations with the complexity term that we're getting there. And we relate this directly to the DC, where now we have only the convexification within of each of the sets, which actually means that for this example that I showed earlier with adversarial rewards, as long as this is convex set, we show that this is as complicated as the stochastic case. We have some improvement in the full information case, and we strictly improve prior results in low rank MDPs, for example, with this, and show that root T is possible. We also use this aggregation approach to have in one specific case of model-free learning. In the stochastic case, this aggregation allows us to get a root T regret bound that was previously unknown. But overall, and additionally, we have some more results, but overall there are a lot of open questions, though. That's really just the beginning, because we still don't know in generality how to deal with the model-free setting, and the rates that we have are far from optimal in the cases where we have it. And still, we had to depart and do specialized algorithms, and it's still open how to get a unified framework and a unified algorithm for these problems. Yeah, thank you.
So we have time for questions. Any questions?
Can you show your upper bound again, the one with the min-max min thing?
You mean?
No, the one before, maybe a few slides. This one.
Yeah.
So, do you know whether this max min term also appears in some sort of lower bound or
Yes,
any?
so the max min term is not only upper bounded by the DC, but it is actually in a lot of cases of interest equal. And the DC term is the one, at least with some localization variant appearing in the lower bound.
No, a lower bound on regret. So, oh, I see. So you know that regret is lower bounded by DC, and then you will do an equivalent to
Exactly.
to this thing. Okay. Cool. Thank you.
I guess maybe I had a simple question. Do we know of examples where we can bound the decision estimation coefficient?
Yes, so typical examples are, wait, let me go to the first slide. So in most of these things here, we can actually bound it. So linear MDPs, tabular, of course, there is low rank MDPs, and I think some low Bellman-Eluder dimension we can bound there. So the part that is not directly boundable is typically the estimation part, which for us is this the term here, this log of the phi class, which is then in the regular one is the model size. This is not boundable, but the DC for most of the classes is boundable.
Oh, cool. Okay, let's thank the speaker again. This concludes this session. We'll a round of applause for all the speakers, and thank you for attending.